so I can present. Yeah, okay. All right. So let's begin. Lazy segment trace. So, well, one thing that is pretty obvious is that a prerequisite to this lecture is knowing what segment trees are. So, I hope most people here know what segment trees are. Yeah, okay, that's good. So, the first problem, or one of the first problems we learn to solve with segment trees, is a range sum point update problem. So in this problem, you're given an array of size n, and you have to answer Q queries of the form A, either you update a value at a given position, or you find the sum of like a range. So for this problem, well, you can also use Fenwick trees, but this is probably like a very common introduction problem to segment trees. I could replace, say, the sum of like a range with maybe the maximum or minimum value, and then I think the only way to solve it is with segment trees, if you want to do it online. So, ideally speaking, you guys should know how to do this because today's lecture is a build up on that. So, do the people here know how to do that? So what I said is that, yeah, Aditya. Okay, yeah, no. So what I said basically is that you guys, so what segment trees do is they can find the maximum or minimum or sum of a range, and they can update points. Like I'm assuming you guys know how to do this because lazy segment trees are a build up on this. So yeah, okay, cool. So now what exactly is the build up? Let me begin by maybe drawing a segment tree. Okay, so let's consider a very similar but slightly different problem where instead of just updating a single position, let's say I also wanted to update a range. So I have an array and I want to be able to update a range by maybe say adding some value, like maybe I add 5 to the range from 5 to 8, and then I also want to query the sum on any range. There actually is exactly a problem like this. This is the first problem we will be covering. You guys can read it over here. So I'll just read the problem as well. Or I can just say it in my own words. Basically, you have to add v to a number in the range of p to q inclusive, and you have to output a line which is the sum of all the array elements between p to q. Those are the two types of queries you need to answer. Problem makes sense. Okay. That's good. So now we're going to think about how lazy segment trees do this. So the thing about lazy segment trees is normally what we do, normally in a segment tree, you only update log and nodes. So let's say I want to update the position at 3. We want to update this, we want to update this, we want to update this, and update this. And there are only log and such nodes which you need to update. So if there was just one index, we'd like really have no issue. But now the thing is, let's say I wanted to update a range. Let's say I just wanted to add 2 to every element. Then in that case, you have to update this. Basically, you have to update every single node in the tree, right? And this is definitely, if we did this in the same way that we did previously, that would be an issue. Now, one key observation to make here is that um, sure, we need to update a lot of nodes, but maybe there's some way to classify the nodes in some way that maybe makes it easier to update them. And so if you guys have attended even values lecture on segment trees, he did cover this in his lecture, but basically a very important property regarding segment trees is that they can decompose any range into log many ranges which are present on the segment tree. Like I can take an example perhaps. Does anyone here want to give me a range?
6 comma
6 comma
7 8.
6 comma 8. Okay, so basically that would decompose to this and this, and so that's an example. Maybe we could take 1 comma 5, that would decompose to this and this. In general, it's true that any range can be covered with log n ranges of the segment tree. So are you guys convinced of why this is true? Because I mean, at first, if I just throw the statement out there, it may seem like, okay, that's kind of random. But the thing is, if you're convinced of the time complexity of a segment tree query operation, that is query on a segment tree takes log n time to execute, then it like naturally follows that every range can be decomposed into log many ranges, because what a query is doing is basically just adding all of those ranges. Now the thing is, this is the interesting part about it. So let's say I wanted to add 2 to 1 from the range from 1 to 8. Notice that all of the nodes that we do need to update all comprise of a subtree of 1 to 8. And if we consider the range we want to update, so let's say I want to add something from L to R, and I decompose this into its like sub segmentary ranges. In every single case, we would have subtrees of the original segment tree. We would have log many ranges, which means we would have log many subtrees. And we want to update every child of each one of these subtrees. Again, now if we try to do so, this might not seem initially helpful, because sure, everything over here is a subtree. I mean, everything over here is part of a subtree, but if we still try to update it naively, it would still be too many nodes. So like, where exactly does this subtree thing help us? Can you guys maybe think about this a little bit? So the subtree thing, I hope makes sense. If not, then like just tell me what is unclear and I'll repeat it. The subtree idea makes sense. Okay. So now the thing about this subtree idea is that like lazy propagation, or the trick that lazy segment trees use in order to make this work, is like very closely related to this idea. And the fact is that if you have, say, a perfect binary tree, number one. Number two, you have like a root node which you want to update every child with like a same value. You can do this in like an efficient way. Can anyone over here think of what that way might be? Or any idea towards where we're going? Okay. No one yet. That's fine. So let's take the example of. Okay, you're typing. Okay, go ahead. Uh, if you want, you can like unmute and say as well, if that would be easier for you. What if we first decompose into the subranges and then add len times subrange interval to the subrange vertex? Len to the subrange times val to the subrange vertex. Hmm. But the problem is still that we need to update too many nodes, right? Like, okay, I want to add 2 to every node from 1 to 8, and each node stores the sum. So I'm going to add 8 times 2 over here, that makes sense. But I'm also going to have to add 4 times 2 over here, 4 times 2 over here, 2 times 2 over here, and there's still going to be too many vertices to update. Well, the idea of adding length of subrange times val is still correct. But the thing is there's going to be too many vertices to update, and that is where the trick comes in. So with lazy propagation, what we do is we say that okay, we want to update everything over here, but does that mean that we have to do it right now? Because for now, what we can say is okay, I'm going to update this, and I'm not going to update this just yet, but I'm going to add some kind of indicator that hey, I need to update it in the future. And then so maybe let's just mark it with a star. Okay. Wait, I'll just. So this range has been updated. These two still need to be updated. Now I'm gonna take a query. Let's say I query what 5 to 6 is. What I'm gonna do is I'm gonna visit log n nodes, right? Because every range can be decomposed into log n nodes. I'm gonna go from here to here, and I'm gonna go here, and I'm gonna see, hey, wait, this hasn't been updated yet. So what I'm gonna do is I'm just gonna update this right now, and I'm gonna say, okay, I need to update these two next because I need to propagate the changes to my children. That's the advantage of everything you need to update being in a subtree. And then this has been updated, and now we're gonna go to 5 to 6. We're gonna say, okay, we need to update this right now, so let's just do that. And then I'll say that okay, my query has been answered. So we'll just update things when we need and delay till then. Exactly. The thing is, every single thing other than the updates is going to be log n time. Like if when we query, oh, we're going to only visit log n ranges, and we're always going to query like if I'm say visiting like this range, that means I have to like visit it by visiting this to this to this. So I'm always going to have visited the parents of the range. So we can be sure that we have updated all of the parents as well. So that is the basic idea behind lazy propagation. Does this idea make sense to the people here? Or do you guys have like a doubt with it? Any questions? Are you sure? If you guys have questions, you can ask because this is not a very standard idea. It's like analogs of this lazy idea in other places. Hmm. I mean, being honest, I haven't seen it, but I would definitely not be surprised if you do see it in other places. Can I repeat? What exactly do you want me to repeat? The explanation, the lazy idea? Okay, so what we are doing over here is I'm saying, okay, let's update the range from 1 to 8 by 2. And now, if we were to do this like naively, what we do is we'd visit the entire subtree of 1 to 8 and we update every single node over here. Like we visit this. We'd visit everything. And this would take too much time because let's say my next query was just subtract 2 from each of them and then add 2 again and then subtract 2 again. This would easily like blow up our time complexity. So instead, what I'm going to do is I'm going to update 1 to 8, but I'm not going to update any of these children. And why am I not going to update the children? Because I don't need to yet. I, but I still need to I still need to keep in mind that I need to update the children. And this is where the subtree property comes becomes very helpful. Like let's say I know that I need to update like a large number of nodes, but I don't know any relation between the nodes I need to update. Then it's gonna become kind of hard to keep track of it. Like let's say I want to update 1, 2, 5, 6, and 3. That's like extremely random. So there's no way to like easily know like from just a little bit of information that I need to update these nodes. But in the case of a range, I know that I need to update every single node which is under the subtree of this node over here, this 1 to 8 node over here. So I can keep track of like a lot of information with very little information. So now what I'm gonna do is let's say my next query was 5 to 6. I'm gonna go to 1 to 8. So from 1 to 8, I'm gonna go to 5 to 8. And there's a star over here that indicates that okay, I know that I need to update it, so I'm gonna update it. And when I know that I'm gonna update it, I also know that I need to update everything in the subtree of this, because initially I need to update everything in the subtree of this. So I'm gonna mark this node and this node as having to be updated. And then I'm gonna go down to 5 to 6 and I'm gonna see that hey, this also needs to be updated. And so I'm gonna update it as well. And then my answer will just be whatever the value of the query is for 5 to 6. So the key thing here is that we visit log n nodes and we update every node as we go, like as we visit it. So at the end of the day, the effect is the same as like having updated it before. But the only difference is we only update it as soon as we need to. Does the idea make sense? Okay. How do we store the indication that we need to update it in the implementation? That is an interesting question. Yeah. How do you store the indicator? So the thing is, so the thing is, you have your original range from L to R, right? You can decompose this range into like your multiple sub ranges. Each of these sub ranges will represent like one particular node on the segment tree, like maybe this node, maybe this node. So what you can do is at the root of this node, you can just store a variable that says, hey, I need to update everything in its subtree. So I need to update everything in, so like when I was doing the update for 1 to 8, I went to both of its children and I said, I'm updating everything in these two things as subtrees. And then when I visit this node, I go to their children and I say that, okay, I'm updating it in their subtrees. The idea is still unclear, most probably. But that is why I'm now gonna present my screen and we're gonna code a lazy segment tree together. And I think that will make it clearer how we do this. Okay. Okay, so I think you guys can see my screen. So let's begin. First, gonna create a node class. This is just gonna store the sum. Also gonna create an operator for this class. So basically, this will be the combine function. I'll create a constructor for this as well. Okay, so far so good. Okay, so the node line is basically if you have you watched Even Values lecture on segment trees? Okay, you haven't. Okay, that's I hope you're still understanding a little bit at least. So basically what I'm gonna store, this is like every node of the segment tree. So if you remember the drawing I have, like I could store it as just like the sum, but this is like just me being more general and saying that I'm gonna store it as a class. And this combine function is basically just is just like adding adding two nodes together. So yeah. So now I'm gonna have my vector. So what we're gonna do over here is we're also gonna make a lazy array. And this lazy array is gonna have a size of A10. Now the reason it's A10 is something you will see while I'm implementing it further. So the first thing is we're gonna have a normal update function. But actually, let's not start with update. Let's start with query because query is more familiar. So TL is greater than TR or L is greater than R or so this is our condition where the ranges have no intersection. Now if our range is completely intersected, then we return. So why do I make this void? It should be if we have a complete intersection, then we just return whatever the value is. Otherwise, we return. Well, we first make our TM variable. And we just return the sum of whatever we have over here. I just realized I need to have return something over here. Okay. So does this make sense? What does node sum mean? Oh, that's just a way in C++ where you can like wait, what are you referring to exactly? Um, this line? Okay, basically this line is the same thing as this, but it's like a compact way of writing it. You know what this line does, right? Hopefully. Okay, yeah, that's good. So did you follow along this stuff? Okay. Anyone with any doubts so far, or should I move on to the query part? I mean, the update part. Okay. So basically, this is the vertex in the segment tree. This is the left range of the segment tree, right range. This is the queries left, right, and how much we need to increment the range by. So maybe I'll call this add instead of update we have because we're adding a value of del to the range. So again, we do the same thing as this. Like if we're not intersecting, then we just return. If we have complete intersection, oh, if we have complete intersection, then what we're gonna do is we're gonna update the lazy value of this by del, and we're gonna return. Otherwise, we're gonna create our tm variable again. We're gonna update each of the subtrees. And at the end, we're gonna combine the changes which we just made. So that's just I'm not 100% sure if this is necessary, but I'm just gonna include it just to be safe. Now I'm gonna create overloads of these. Does everyone over here know what overloading functions is? Okay. So that's the add function. Now, so far, this is just when your regular secretary stuff. Now I'm gonna code up the actual lazy propagation logic. So for that, we're gonna create a function called lazy update. You can call it whatever you want, but I like to call it this. So what this is gonna do is, so many of you guys asked where I'd store the indicator that you need to perform a lazy update, and that's going to be indicated by this array over here. So if this array has a non-zero value at like a particular vertex, that means I want to update it. So what we're going to do is this condition is actually not necessary, but I'm just going to include it for the sake of like emphasizing stuff. So this means if we need to update this, we're going to go ahead and update it. And the reason I'm multiplying over here by tr minus tl plus 1 is because, oh wait, it's segv.sum, okay, is because I need to, they're storing the sum in each of the things, and there are going to be exactly tr minus tl plus 1 different values that we need to add lazy v to in this subtree. So I hope this makes sense. Then we're also going to propagate the changes. And we're finally going to set lazy v to 0. Now the thing is, we don't need this if condition, because if lazy v was 0, this would just become 0 times anything, which is 0. We just add 0 over here, we'd add 0 over here, and we'd again set it to 0. So I'm going to remove the if. Now, all we have to do is, before like performing any operation, we just have to include this lazy update. So before the query, I'll just add this lazy update. Before the add, I'll add this lazy update. Over here, I'm going to add the lazy update because we need to propagate it to its children. The indicator that we need to update them. And I think that should be it. I think this should be our entire lazy segment tree. Oh, what did you want me to repeat, Chess Coder? It's clear now? Okay. I'm just gonna go to that SPOJ function, SPOJ question, and I'm gonna try to implement it right now, just to check if my segment tree is correct. Okay, if type is equal to 0, we have PQV. I hope this part is like people are understanding what I'm doing here. I'm just coding up the actual question. Okay, does that work? It does not work. Okay, what is going wrong? Oh, okay, this condition is messed up. It should be L less than equal to TL and okay. I think that's the mistake. Okay, so basically what I did is what we need to check is that the segment tree node perfectly intersects with our range. And before I was doing the other way around. I think that was the mistake. Does it work with that? Okay, there's still something wrong. This should be R. This should be L. Okay, I also did not check the intersection conditions properly, which is a little bit sad. Does it work now? Okay, it does work now. Okay. Hmm. So I think this is correct now. The thing is, I don't have an SPOJ account, and I actually tried creating one, and it did not go that well. So what I'm going to do now is I'm just going to send Ovian this code, and I'm going to ask him to submit it in my behalf, and let's see if it ACs or not. I hope everyone here understood what mistakes I made, by the way, or is that not clear? All right. Okay, Ovian is currently in the process of submitting the code. Okay, unfortunately that did not work, which means there are still some mistakes, which I will now try to find. Hmm. Oh, wait a minute. Do they use zero-based indexing or one-based indexing? They do use one-based indexing, which means that probably isn't the issue. Hmm.
Could you say a name on the Discord server?
Okay, just give me a second, guys. I think this should work, but 0-1 indexing bugs. Yeah, I did notice the 0-1 indexing thing. I am not sure if that's the issue or not, but what I'm gonna do is okay. Hmm. I mean, let me ask him if this works. I am using LL, so integer overflow should not be an issue. So lazy update is supposed to be right before you do anything. So it's supposed to be here. It's supposed to be here. And the thing is, I'll put it over here. Oh, okay, now it is accepted. That's very weird. The only thing I... That's nice. Yeah, Ovian just said that this did work. The only thing I changed is I changed this from a 1 to a 0, which honestly I don't see how that should make a difference because in the original question they were using 1 based indexing, but um yeah, apparently that fixed it. 0 to n minus 1 and 0 based indexing. So the thing is, if I'm doing 0 to n, that's basically like having n plus 1 nodes, but I don't see how that should make a difference. But this code is correct now. So if you change n to n minus 1, it should work. Now the thing is, I don't have an SPOG account, so I can't really submit it. But I'll copy paste this code and yeah, I'll just send this to you. Maybe I can. What do I? Paste pen? Okay. Hmm. Well, so anyway, that does cover this problem. I did get AC, which is good. So this is correct code now. Uh, okay. So now the thing is, let's say I wanted to make some slight changes to the segment tree. Like in normal segment trees, what you can do is you can find the minimum value of a range as well, not just the maximum value. I mean, sorry, not just the sum. So all of the changes that would happen over here and over here. So the first change we do is instead of having the sum over here, we would have a variable called min. We do answer.min is equal to the min of this and min. One more thing we need to change is over here. Well, over here I'm not really changing stuff. I'm more like adding another functionality to it. So over here, notice that I'm not multiplying by this. Can anyone over here tell me the reason for that? But this code is complete. Now, with all of this, the segment tree can also find the minimum value. Like this code is complete. Just a few more lines and it can also find the minimum value. But notice that over here, I haven't multiplied by this when adding to this. So can anyone over here tell me why? Iterated min is just number of iterated. Min iterated addition is multiplication. Yeah, I mean, exactly. The thing is, if I'm adding to a range and I'm increasing, like, let's say I had a range like 1, 2, 3, 4, 5, and I increase every value in this range by like 2. If I want to find the minimum value from 1 to 5, the answer would be 3, which is just 1 plus 2. But if you had addition, you'd have to add 2 5 times because you're adding it for every element. That's why we're not multiplying by tr minus tl plus 1 over here. Does everyone know why we are multiplying by tr minus tl plus 1 when you want to find the sum? Yeah. Okay. That's good. Okay. So that was the implementation. I will continue presenting with my iPad now. Okay. I know 2024 P2 be done with lazy propagation. I am actually not sure because I haven't got an AC on INOI 2024 P2. I could ask Ovian, but I think he did something with a range DP, if I'm not wrong. Oh, Ovian Gandhi. And he actually got like the highest, not the highest, the second highest. He got like 81 on that problem. So okay. So the next thing we're gonna cover is this problem. So the difference between this problem and the previous problem is that this problem doesn't just have range add, it also has range set. So you guys should read this problem. So basically the problem summarized is just you that is basically the problem. Yes, this is the CSS one. Okay. So does anyone have any ideas for this? How we go about solving it? Any initial thoughts or anything? Two lazy arrays. Two lazy arrays is indeed correct. You are thinking in the right direction. So does anyone understand why we need does everyone understand why we need two lazy arrays? So one of them would be for the add operation, and the thing is add and set are like completely independent of each other, right? So that's why we have two arrays. Because you'd have to deal with them separately. Okay, so Nishkarsh's idea is that we check, you keep two lazy arrays and you check for both in the lazy update function. Could you give me like a skeleton of how your lazy update function would look? Or does anyone else have any ideas of how we'd have to modify the code for it to work with this? So I'll give you a hint. The two lazy arrays thing is correct, but that's not all. There is something else as well. If you have two arrays, lazy one and lazy two, we still need to know in which order we need to iterate through both of them. Okay, so consider the thing like number one is like the thing is some operations will be some operations, update operations will be I mean set operations will be set operations. If you have like maybe multiple things that are like summed up and you apply a set operation immediately, then what happens to the yeah exactly. Oh, Avian Gandhi, that is correct. If you when you whenever you apply a lazy set, any lazy adds are instantly overwritten. What Nishkosh is saying is that maybe you have like a lazy set and then you have ads. So how do you know that you won't overwrite the ads which you have afterwards? And the thing is, this doesn't happen because of the way you visit the nodes. So you apply the lazy update function every single time you visit it, and when you're like applying the new update, you're gonna have already applied the previous update because you have to visit the node to apply the new update. Does that make sense? So the key thing to notice here, which basically solves the entire problem, is that if you have a set operation, it will instantly overwrite any previous add operation. So I'm just gonna present again. Oh, this is just to like show the changes that I have to make to my function. So what I'm gonna do basically is I'm gonna make my current segment tree to like a segment tree that will work for this. So the first thing is we'll have two lazy arrays. So for that I'm gonna create an enum. You can do this in whatever way you want, but I'm just gonna put it like this. I'm gonna remove the min for now because that just adds more stuff that I need to take care of. Now the thing is over here, we're gonna initially assume that we set each of these to -1. Because the thing is you can set the value to 0. So -1 is gonna like indicate that there's nothing over here. So now if lazy v set is not equal to -1, that means that I have to set it to something. So what I'm gonna do is I'm gonna set it. Oh, oops. This should be 2v, this should be 2v plus 1. Now the thing is, oh, I forgot to write sum again. Okay. Now the thing is, like, wait, is there anything? Oh, right. It is multiple arrays now. Okay. Okay. Now the thing is, like Ovian mentioned, we also need to set the value of lazy add to 0 as well. Wait, actually, you don't have to set this. You just need to set the children. Okay. Let me set this to -1, 0. And now we do the same thing over here. By the same thing, I mean, like, this is going to be pretty much analogous to our previous code. And yeah, this should be the new lazy update function. This right here. Now over here, what we do is we'd set in the add function, we'd just add this to here. For our set function, I'm just gonna copy paste this because the majority of it is gonna stay the same. Change its name to set. Maybe I'll change this to X as well because it's no longer a delta. And we're gonna change plus equals to equals. And we're gonna change add to set. And we're gonna update this to 0. Very important. Or actually, wait. Yeah, I think this should be right. And everything else should remain the same. Okay, so does this make sense? This will work for this. Let's go to the CSAS problem. I'll try to see if this works. Oh, does it make sense to everyone so far what I've done? Any questions? Any doubts? Okay. If type equals 1, we have ABX. We need to increase every value by from A to B by X. So that should be add. Otherwise, we have ABX, we need to set every value in the range. So this should be that. And otherwise you have AB. I need to output the sum from A to B. And this should be that. Q is already. Oh, okay, it gives the correct output. Let me try to submit this. Okay, and it does work, fortunately. Okay, so I'll just share the code. So that is how we solve that problem. Again, I'm asking, does anyone have any doubts with what we did? As a quick recap, the main observation over here, the main thing boils down to the lazy update function, how that changes. And that's pretty much it. So our observation was that if we have a set operation, that overrides any existing add operations that were there. So over here, as we're applying this set operation, we're also setting the add operation to 0 over here. And besides that, everything remains the same. I created a separate add and set function as well. So the add function looks basically identical. In the set function, I set this equal to x, and I set the add equal to 0. And yeah. So does that make sense? Can I see thumbs ups, thumbs downs? Okay, Yemen letter, do you have a doubt or? Okay, excellent. That's all right. So that was the second problem. The third problem is a little interesting. So this third problem is called polynomial queries. It's another CSS problem. I'll send it here. You guys should read the problem right now on your own. So the reason I thought this problem is interesting is because we can consider one variation of this problem where instead of finding the sum from L to R, I say just find the value at a particular point. So I want to find the value at index I after having these updates. Can anyone think of a solution for that? Did you guys understand the slightly easier variation of this problem that I just asked? Or do you want me to repeat it? Okay. Hmm. Okay, I don't want to spoil the solution, so does anyone else have an idea of how you solve this? Not where you have to find the sum from L to R, but let's say I change the question to I just want to find the value at an index. Do you guys want a hint, maybe? Okay, Cheskoro does not want a hint, Neshkosh does want a hint. So maybe I'll wait for 1 to 2 minutes and give a hint then. Okay, yeah, so think about it. Okay, so my hint to you guys is let's say the update was slightly simpler and you guys didn't know what lazy segment trees are. Let's say I had an update where I update L to R, so I just add X to L to R, and then I want to find not the sum from L to R, but just the value at a particular index. So basically, this is like you could consider this as an easier version of the original first problem that we covered. So are there any ideas for that? Okay, so since I don't see any ideas, I will spoil the solution. Basically, for that problem, the intended q log n by brute force basic sec tree. So what exactly is the sec tree? Okay. Well, the thing is, I do use this actually in my solution. What I do is I maintain the difference array rather than the array. And then when I want to ask for what an element at a particular point is, that is like basically equivalent to saying what is the sum of the first I elements in the difference array. Yeah. So do you guys see how we could use difference arrays over here as well if you just wanted to query one point? So basically, you have to use a lazy segment tree along with the difference array because updating 1, 2, 3 in differences is like updating by a fixed value for a range. Now the thing is, the solution for this isn't actually that complicated, and in fact uses a very nice trick. So let's say I have a range from L to R, and I want to fill it with 1, 2, 3, 4, 5, and 6. So what we're gonna do is we're gonna try to like decompose this update operation over here into something simpler. So what I could do is I could first of all divide this into two parts. I'm first gonna add 1, 2, 3 over here, which is the same operation, but it's just on a smaller array. I'm gonna do the same thing over here where I add 1, 2, 3, but I'm also gonna add 3, 3, and 3 over here. So I'm gonna add two things over here. I'm gonna add this, and I'm gonna add this. Because if I add 3 to each of these, it just becomes 4, 5, 6. So this, when I add this 333 over here, this is the same thing as your range add. Okay, yeah, I'll repeat. So basically, this is the problem. You know the problem, right? You need to update a range from L to R by like 1, 2, 3, 4, 5, 6. So what I'm gonna do with this is I'm gonna try to split it up into like smaller updates of the same type. So the way I've done this is I'll first of all split the range in half. Now said I can say that this is the same thing as updating the left half of the range by 1, 2, 3, the right half of the range by 1, 2, 3, and then 3, 3, 3. So these two things where I updated by 1, 2, 3, it's the same thing as the original operation. So that's like very easy to keep track of. And this 333 thing is like a range add, which we've already seen like multiple times how we can do that. So the solution for this problem is to again have two lazy arrays. One of the lazy arrays is for the special new type of operation, and one of them is for your range add. And while we don't have any range adds in the original question, while we're decomposing our operation, we are going to have range adds in their decompositions. That's why we have range adds over here. So does this idea make sense? Ovian, if it what part would you like me to explain better? Okay, how do we store 1, 2, 3? So the thing is, maybe one more thought that might have occurred to you while thinking of how to decompose this is you could maybe say that one half will store 1, 2, 3, the other half will store 4, 5, 6. And what I store in this node is that I need to start at 1. What I store in this node is I need to start at 4, and I lazily propagate those downwards. Did anyone over here think of that? Okay, if not, then did anyone? But did you actually? If not, then do you at least understand what I said? You did not understand what I said. Okay. So basically, what I'm saying is in your lazy array, what I said right now is I'm going to decompose this into 1, 2, 3, 1, 2, 3, and 3, 3, 3. But instead of that, maybe I could have said that instead of that, let's just decompose it into 1, 2, 3, and 4, 5, 6. Because then I'm not involving this other like range add thing, which seems kind of unnecessary, right? Now, the thing with this is we're going to have to keep track of where we start. And if you want to keep track of where you start, you're going to have to not just have a lazy array, but you're going to have to have maybe like a lazy array of arrays, where every lazy v would be like an array of the different places where we start. And that would like, yeah, in a way it would be that. And that would become very annoying to deal with. And it would also not be fast enough. So now if you did think of this, then one way to like get rid of this thing where we have to decide where we start is to just say that we always start from 1. So what our first lazy array is going to store is it's going to say that we want to update this range. So maybe you could say lazy of our special operation is just going to say that like how many times we need to add 1, 2, 3 to our range. So maybe if this was 2, that means we need to add 1, 2, 3 to it twice. If it was 1, it means you need to add 1, 2, 3 to it once. Does this make sense? On the other hand, if we have our range add, that's just going to be normal. That's just going to be the value that we want to add to the range. And notice that this stacks very well as compared to this operation. This operation stacks very well on top of each other because we can just add the values and it would work. Does that make sense? What is lazy OPV store? So OP over here represents our special operation. So this operation where we update L to R by 1, 2, 3. On the other hand, let's like lazy of add V would store the range set operation. So I'm saying that lazy of OPV being 1 means that I add 1, 2, 3 to this range with the range represented by V one time. If it was 2, I would add it 2 times. If it was 3, I'd add it 3 times. So if it was 2, then that would be like adding 2, 4, 6, basically. Does the idea over here make sense to the others? Or what exactly did you guys not understand? Coding it out would make it clearer. Hmm, perhaps. Yeah. Um, so for this problem, is it fine if I just write the code over here? Because being honest, I don't really feel like coding it out. I will write the lazy update function because that is like the main important thing. So what we're gonna do is we're basically gonna say lazy of OPV is gonna be representing our special operation. If this is not equal to 0, then we're gonna set segv. We're gonna update segv. By it into the size plus 1 divided by 2, where the size is just equal to tr minus tl plus 1. So this is just n into n plus 1 by 2 being the sum of natural numbers. Then what we do is we propagate the lazy downwards. So we update lazy of OP2V and 2V plus 1. We just add the value of this. And now we need to do the range set. So that's gonna be, and we're only doing this to the right vertex, by the way. That's why I only have 2V plus 1, because we only have to add the range add to the right side. So this is gonna be plus equals lazy of OP V into the value Tm minus TL plus 1. Over here, Tm is just equal to TL plus TR divided by 2. So this is just gonna become, like, over here, it's just gonna become 3, because our range would be 1 plus 6 and our middle value would be equal to 3. So we just have 3 minus 1 plus 1, Tm minus TL plus 1. This is for OP. The add one would look the exact same, except we've coded that multiple times. So I can share my code, yes. This is my code for it. Although my coding style was quite different before. What would be the rating of this problem if it was on Codeforces? So just the fact that it uses a lazy segment tree and it uses a non-conventional application of it. I would probably say it's like around 1900. That is it indeed, yeah. That's pretty much solves the problem. Oh, the rating. Do you guys think it should be higher? Maybe 1900 is too low. I'm not 100% sure on this. I could see it being 2000 as well. Yes. Hmm. Yeah, no, that is possible now that you mention it, because data structures do come at higher ratings. Do you guys want me to code this? Because I mean, I guess I could code it. Uh, did everyone else understand? Okay, do you guys want me to explain the CSCS code? Anyone here, or is it clear? Okay, I will explain the CSS code then. Cool. I will just start sharing my current screen. Yeah. So this is just the normal stuff. The query function also looks the exact same. This update function is slightly different. So basically what we're doing, so let's first focus on this function. This this is the lazy update function. So first we store a variable called n, which is just the size of the range. We add the value of, so lazy 0v represents our special operation. We add lazy 0v into n plus 1 by 2, which is just the value of the sum of the first n natural numbers to our current segment v. We propagate both of these changes downwards. Like I said, if you have 1 2 3 4 5 6, you'll first propagate 1 2 3 and 1 2 3 to the left and right children. Right. Does that make sense so far? Yeah, okay. Now over here, we're adding, so lazy 1 represents the range add, not the polynomial type of update. So over here, I'm only doing it to the right child, because if you remember in the explanation, the plus 3 comma 3 comma 3 was only needed for the right child. The left child was fine. So just a 2v plus 1, I'm adding lazy 0v into tr plus tr by 2 plus 1 minus tr. So this number basically just represents the value 3 in our example of 1 2 3 4 5 6. So this over here is tm. That's like the middle value of the range. I'm subtracting TL because I need to start at 1 regardless of where TL is. And I'm just like trying to get the size of it and try to find the middle of the size. So you guys can figure out like how you get this later, but does it like at least make sense like structurally? But this is like the middle value, and I'm subtracting the beginning, so that kind of gives you like the middle value of the range. Yeah. And then okay, this part over here is just the normal range add, where if this is not 0, I add this times the size. I propagate it to both the children and I set it to 0. Over here, what I'm doing is I'm just adding this to segv. So this is the sum of the natural numbers. This is I'm propagating it downwards. I'm just doing plus plus over here because that represents that I'm doing the operation one time. I'm adding TL minus L to lazy 1 of 2v and this to this. Okay. So does that make sense? All right. So with those problems, that is all I wanted to cover. I hope you guys understand lazy segment trees slightly better now. A written resource for this lecture will also be available after the lecture gets over. I've included the problems over there. I've included my code over there as well. You guys can also, of course, submit the problems. Try to get AC yourself because that is the best way to understand, of course. My handwriting is better than before. That is very nice to hear. That is very nice to hear. And a problem not related to lazy secretaries. Could you just DM it to me? I will look at that after the lecture and I will try to answer that problem. It's a concept. Um, okay, go ahead. Moore's algorithm. Okay, I'll just stop recording because this is not related to the lecture. So from this point, the lecture is like basically over. Thanks for attending, guys.